Hello, we will now talk about Chapter 7, Section 1. Chapter 7 deals with sampling distributions, and it is a concept that really the rest of the year is based on, and we'll be using sampling distributions in every other chapter the rest of the way. And chapter 7, Section 1 is mainly just the terminology that goes along with it and just the concept of what is a sampling distribution. So let me try to explain that to you. Many of these concepts we've been talking about throughout the year. And so the first thing is the concept of a population. The population is the whole group we want to know something about. And as a matter of fact, let's go ahead and write that definition. So the population is the entire group you want to know something about. And the population can be made up of people, animals, or things. People, animals, or things. So it could be, you want to know the percent of people that are going to vote for a presidential candidate. So your population would be every voting person in the United States. Or it could be you have a warehouse full of boxes. And so the population would be all the boxes in the warehouse. But let's say, for instance, our population is this, all the trees in this forest. So this circle represents all the trees in a particular forest. And let's just pretend that there's 20,000 trees in that forest. So that would be our big N. Big N means population size. So there's 20,000 trees in this forest. All right, now we couldn't, and so then we have the concept of a parameter. And a parameter is just a value that describes the whole population. So the parameter, let's say, would be the mean height of the trees. So let's just pretend the mean height of the trees is 31.7 feet. That's what we're trying to, to find out. All right, so a parameter is just a value that describes the whole population. The whole population. So most of the time, it's either going to be a mean, which we call a mu, or a proportion, which we call a p. So like mu would be like the mean height of the trees, or the mean weight of the trees, or the mean number of fruit created by the trees, something like that. But it could be a proportion, the proportion of trees that are pine trees, or the proportion of trees that have a fungus, or something like that. But let's pretend that we want to try to figure out the mean of the trees. And so what we could do to find this value is we could take a census and measure the height of all 20,000 trees. But what we decide to do is we decide that's not practical. And so we're going to take a sample, a subset of this. And so let's just pretend we take a sample of 50 trees. And so that's our little subset. That would be this little smaller thing here. And those are the 50 trees we selected. Of course, it's critical that we get those trees randomly, so to prevent bias. And so there's our sample. And so our sample is just going to be the subset of the population, is a subset of the population that we actually study, we actually measure. Okay, and we come up with a sample mean. We measure the heights of those 50 trees and average them. And let's pretend, that this one, the sample mean is like 32.58. Okay, we don't expect it to exactly equal mu just because of random chance, or what we call sampling variability, even though we've gotten a good random sample. And so that's what a sample is. And then this value here, this X bar, that is what we call a statistic. So a statistic is a value that describes a sample. And so that can, now if it's a mean, it's X bar, okay? Now X bar and mu are both means. Means the mean of the whole population. X bar is the mean of the sample. So X bar is an estimate of that. It estimates mu. And then if we found a proportion, that would be p hat. Our p hat would be a sample proportion that we are using to estimate a population proportion. All right, and so then we have the concept of a sampling distribution. And so let me try to explain that. Now, the thing about it is we took one sample of size 50 and got that X bar is an estimate. But what if we took another sample of size 50, took a sample, another random sample, we get another X bar, and it's almost certainly not going to equal that just because of sampling variability. And I measure the height of those 50 trees and average them. And so let's just pretend that's 29.94, let's say. And so that's another. And then if I took another sample, a third sample of size 50, found another X bar. And so once again, it's going to vary. So let's say it's 30.72 feet. All right. And if we kept going on, so let's graph this situation here. There's my parameter, my mu, the average height of all the trees in the forest. That's my mu. And so my first X bar is going to be somewhere like up here. And then we get another X bar and another X bar. And if we kept going on and getting more and more X bars, okay, and if we found every possible value of X bar that we could possibly get, if we kept just doing repeated samplings, all of the same size from the same population, all these values of X bar are what we call a sampling distribution. A sampling distribution. And it's going to vary. These X bars are going to differ because of what we call sampling variability. So sampling distributions, in terms they use the proper, it's very important to use the proper terminology. This is not the sample distribution. It is the sampling distribution. The sample distribution, like for this sample, would be the heights of these 50 trees. That'd be the sample distribution. The sampling distribution is every value X bar could possibly take in repeated sampling. And so what is a sampling distribution? It is every value that a sample statistic, and once again, a sample statistic for us, most of the time is going to be either X bar or P hat, all right, can take in repeated samples of the same size from the same population. So let me show you, let's talk about, so the first thing is this would be a sampling distribution for means, okay, like that. But let's talk about if we had it for a proportion. So let's say if we didn't want to know something quantitative, we wanted to know a proportion. Let's say if we were estimating the proportion of all of these trees that have a fungus, and let's pretend when you look at all 20,000 trees, let's say the proportion that has a fungus is like 18.1%, so 0.181. And that's what we're trying to estimate. In order to find this number, we would have to measure, we'd have to study every tree in the forest, but we decided to take a sample, a subset, and let's say of 100 trees, okay, of 100 trees. That's our sample. Within our sample, we notice, like, let's say 20 of them. So 0.2, that is our estimate. It's not going to exactly equal that. As a matter of fact, it'd sort of be impossible with this sample size because of sampling variability. And then if you took another sample of size 100, another sample of size 100, find another P hat. So it's, it may be like, 0.16, okay, in that sample. It's going to vary because of sampling variability. And so what's happening here is our parameter of 0.181, so that's our P. And so our sample values are going to vary around that. And if we get good random samples, that prevents bias. And it means these P hats are going to be bunched around. They're going to be bunched around the true population value. In other words, the parameter. And so that is a sampling distribution of P hats. It is every value that P hat could possibly take in repeated sampling. So anytime you get a sample value, anytime you get a statistic, a P hat, or you get an X bar, okay, you should always say to yourself, hey, it's just one of many I could have gotten, like that. And that's what a sampling distribution is. Now, by the way, these are the main two ones we look at, means and proportion, but there's all sorts of parameters in statistics. I mean, we could find the population standard deviation, which is shown in your book. Okay, that would be sigma, and use S to estimate that, okay? And we could have a sampling distribution of, find the standard deviation of all the sample, all the different samples, and that would be a sampling distribution of standard deviations. Or we could find the median, okay? We find the population median. Let's just pretend the median number, in here is a tree that's, let's say 32 feet tall. Okay, and then you could find the median for all the different sample values and come up with a sampling distribution of medians. Okay, so there's all sorts of sampling distributions, but these are the two that we are going to primarily work with this year. Now, what do I mean by an unbiased estimator? Well, if we've gotten a random sample, if we've done things right, all right, so an unbiased estimator means my X bars are going to be centered around the true value. So let me give you an example of something that would be a biased estimator. Let's say if you wanted to estimate the proportion of people in a particular city that associate with the Republican Party. And let's say in this one particular city, it's like 45% Republicans. That's the P I'm trying to estimate, okay? And so I take a sample of, 100 people, but I do this. I actually go stand on a street corner in a very conservative part of town. It has a lot of Republicans in. And so I'm likely to get a P hat that is, let's say, too high, okay? And if I did this again and again and again, it'd be creating my sampling distribution. So here's the true population value, 0.5, but I'm using a bias technique. And so that all my possible values of P hat are too high, okay? To where the average of my P hats is going to be off of the true value. It's centered in the wrong place. Now, there may be like one value of P hat that's close, okay? But in general, they're averaging something. The mean, if I average these P hats, they are not equal to P. And so that is an equation that displays bias, when the mean of your statistics is not equal to P. So that's what that looks like when you have a bias method. It's not that one of your P hats is different from P, it's the average of all of them. So if it's an unbiased estimator, that means the mean of your statistics is going to equal the mu. So unbiased means, an unbiased estimator means the mean of your X bars is in fact equal to mu. And the mean of your P hats is in fact equal to P. So when we say it's an unbiased estimator, it means the average of all the statistics, all the possible statistics equals the true population values. All right, so now let's talk about how bias and how variability works. And we're going to do some activities in class that can show this. All right, so high bias, let's draw these four graphs. So if you have a sampling distribution that has high bias and high variability, what does that look like? And and I'll do it with means. And so what that means is, so here's my mu, like that. Well, that means if I have high bias, high variability, it means my X bars are really spread out, which typically means that I have a really big sample. I have a really small sample size, rather, because a small sample size creates a lot of variability. And you'll notice the average of my X bars does not equal mu. So that's what bias is, okay? High variability means they're really spread out. Let's say if I have this, what is low bias? Low variability. Well, low variability means they're all compacted together. Okay, so here's the true value, here's mu, and low variability means they're all bunched together like this. So low variability, so what this means is I've had a nice big sample size that's created a low variability, and I've done things in an unbiased way. All right, so low bias, low variability means they're all bunched around the true value. But what if you have high bias? In other words, the average of your X bars is away from your mu, but low variability. Okay, so you have a really big sample size that creates your low variability. So here's my mu, but you've done things in a biased way. It means your X bars, the average of your X bars is away from the true value. So the average of your X bars is not equal to mu. Okay, so and then lastly, let's say if you have low bias and high variability, these things are really spread out. you had a really small sample size, but they're all centered around mu. So you did things in an unbiased way, but you just had a really small sample size. And so you'll notice how the average of the X bar is equal to mu. And so that's your different pictures of bias and variability. Bias means your average, once again, the average of your statistics is equal to mu. Variability means, high variability means they're really spread out. Low variability means they're put together. And it's important to know these low variabilities. How do you create low variability? By a big sample size. Okay, if you got a really small sample size, your X bars are going to be really spread out a lot. All right, and so this terminology is important to be able to understand this. Describe what is a population distribution. A population distribution is in essence every value in the population. So this would be every value in the population. And we're going to look at some examples to illustrate this. And so like for this particular one, for like these trees and the heights of the trees, the population distribution is the height of all 20,000 trees, those 20,000 numbers. You know, distribution is just a list of numbers. Okay, so a population distribution will be every number in the population, the height of all the trees. All right, what is a sample distribution? It is every value in the sample. It is every value in the sample. So the sample distribution, like in this example, would be the heights of these 50 trees that were in the sample. So you would be 50 numbers, okay? So that would be the sample distribution. All right, and a sampling distribution, as we've set up here, it is every value a sample statistic can take in repeated sampling. If we did many samples, it is every value that a statistic, and a statistic for us is almost always going to be X bar or a p hat. Okay, an X bar or a p hat. So that's what a sampling distribution is. So know the difference between those terminologies there. All right, let's look at a couple of examples that will hopefully help out. So in context one, this one deals with means. It says a college professor wishes to estimate the mean amount of time that students at his college spend sleeping each night. So it's you see the word mean, so we're dealing with a mu. All right, there are 7,214 students at the college. Okay, so that would be our big N. That is our population size. All right, unbeknownst to the professor, the mean time that the 7,214 students spend sleeping each night is 7.11 hours with a standard deviation of 0.91. So that is a population value. That is mu. Mu is the mean of the whole population, not just of the sample. X bars are the sample. So our mu is that, and that is our population standard deviation. That is sigma. So that would be another parameter. Takes an SRS of 40 students, all right, gets a mean sleep time of that. So that would be our sample mean. That's our X bar. Okay, and then with a sample standard deviation, that is what we call S. Okay, so identify the following: the population, the whole group we want to know something about, and that would be all 7,214 students at this college. That is the whole group we want to know something about. What is the sample? That would be the 40 selected students. Those are the ones we're actually studying. Okay, the 40 selected students. Okay, the sample is what's in, it's what's in there. Not their sleep times. Okay, it's what is in the sample is the 40 selected students. All right, so then we've got, what are the parameters? Now in this case, we've got more than one parameter. All right, we've got a mean and a standard deviation. Parameters are just values that describe the whole population. So we've got two of these numbers. We've got mu, that's a population value, and we've got sigma. And so those are our two parameters. So mu, so we've got mu, which is equal to 7.11 hours. And then we've got our sigma, and that's equal to 0.91 hours. Those would be our two parameters. Now, what are our statistics? Our statistics are going to be the numbers that describe the sample. And so that would be the 7.16 and the 0.88 hours. And so that would be the X bar, the sample mean, which is 7.16 hours, and the S, which is 0.88 hours. And so the X bar is going to be an estimate for that. And this S is an estimate for sigma, okay? And if we looked at every possible value of X bar, that would be the sampling distribution. If we looked at every for the mean, and the sampling distribution for the standard deviation would be every value S could take. What's the population distribution? The population distribution is every value in the population. So it would be the sleep times for all 7,214 students for the whole population. And we're not going to, and if we looked at all of those, that would be a census. But we're not doing a census, we're doing a sample. What is the sample distribution? It's the values in the sample. And so in this case, it's sleep times for the 40 people. And so it would be the sleep times for the 40 students in the sample. And then what is the sampling distribution of the sample mean? It is every value that X bar could possibly take. It is every value that X bar could take in repeated samples of the same size from the same population. Okay, so we've got a mu, which in this case is 7.11. So here's our mu, 7.11. The sampling distribution is every value X bar could take. If we took many, many samples, every value X bar could possibly take. So this family of X bars is what we call a sampling distribution, okay? And by the way, one of the things we're going to talk about in the next couple of sections, what does this look like to you? That's right, it looks a little bit like a normal curve. These X bars would be approximately normal as long as your sample size is large, bigger than 30 or so for means. And we got a different thing for proportions, but that's what a sampling distribution is. Every value X bar could possibly take. Now the one we got was 7.16. So that's just one of the X bars, okay? But if we did many, many samples, so that would be that. So now let's look at an example with proportions. So this says the professor in part one also wants to know the proportion of the 7,214 students that attended a public high school. Unbeknownst to him, 6,142 of the 7,214, which is 85.1% about, attended a public high school. He takes an SRS of 250 students and finds that 202 of them, which is 80.8% roughly, attended a public high school, okay? So once again, our population would be the same sort of thing. Now, let me also say this to you. One of the things that people can get a bit confused by, with these proportion ones, they can give you this data in a couple of ways. They could give you the X and the N, okay, or in essence, or they could give you the percent itself. In other words, they might just tell you just the percent there, or they might not tell you the percent and just tell you the fraction. So you kind of have to be aware of that. So our population, once again, is this, the whole group we want to know something about. So once again, that's the same thing. All 7,214 students at the college, students at the college. Okay, what is the sample? The sample in this case, they selected an SRS of 250 students. So you would say the 250 selected students. Okay, what is our parameter? So our parameter of interest is a proportion in this case. That is what we care about. So our proportion is P, and it's 85.1%, which is 0.851. And you could list it as a percent, you could list it as a fraction, or you could put it as a decimal like this. Okay, what is our statistic? That is our P hat. That would be our value describing the sample. And so that would be this 80.8%. That is the proportion in our sample that attended a public high school. So that's that. What is our population distribution? This is a trick question. For proportions, that's in essence every value in our population. Well, the thing about when you're dealing with categorical data like this, the population distribution would be every value in the population, but they're all either in essence a success or failure in this regard. It's either public school or not public school. So there isn't one. There isn't really a population distribution for proportions, okay? Because it's not like with a mean where everybody in the population has a different sleep time, has a different number. Here, they either went to public school or not, so it's really not a distribution. And the same thing with a sample. In regards to a proportion, there isn't a population distribution, or there isn't a sample distribution. Like here, it'd be if it was quantitative, everybody's got a different sleep time, okay? But when you're dealing with this, it's just they either went to public school or not. So that's not really a distribution. That's not a list of numbers, so to speak. And then lastly, what is the sampling distribution of the sample proportion? It is every value p hat, that is our statistic, could take in repeated samples of the same size, with the same population. And so the sampling distribution of this. So here's our parameter, RP, which is 0.851. So we got one sample that was somewhere down here, our p hat. But if we took many samples and found many different p hats, and if we kept going on and we took every possible sample that we actually could, sort of theoretically kind of getting an infinite number of samples, all right, all these possible values of p hat, we call them a what? What do we call that? A sampling distribution, okay? It is every possible value p hat could possibly take. And that's it. That's section 7.1. And if you have any questions, please send them to me. Thanks for watching the video. And I just hope you have a great day.